Hello, my name is Aaron Mazzeo, and today for lab number 4 we are going to explore the use of the finite difference method with the heat equation. The example we have is that of cooking a turkey. We're going to suggest that the turkey has certain thermal properties with which we are now familiar. We're going to say that the turkey might be a 15-pounder, and if compressed into a 3D cube would have side lengths of 19 centimeters. The, the turkey has been thawed slightly, so we're going to say that it is having an internal temperature of 10 degrees Celsius, and we're going to set the oven to 325 degrees Fahrenheit or 436 Kelvin and look at the temperature distribution in the turkey over time. We're going to do this with 1D and 2D simulations, and our ultimate goal is to get an idea of whether or not we are cooking the internal portion of the turkey to a safe temperature of 165 degrees Fahrenheit. Let's go ahead and get started. We are going to begin by opening up an editor window in MATLAB and then typing some of the basic commands that we're familiar with at this point to get our space situated. For this problem, we're going to use a time step of 10 milliseconds or 0.01 seconds, and we can change that later if we like and see what happens with respect to convergence. The mesh size is going to be pretty small, at least in the 1D case, which we're starting first. So 1 millimeter. We're going to run our simulation for hours, and we'll start by running it for 4 hours. So in seconds, that will be given by the following. I think that comes out to 15,000 something seconds. The number of cycles can be determined by dividing the total time of our run by the time step. And this will be the number of cycles. We're going to plot our results every 900 seconds. That may seem pretty long periods of time to go without seeing anything, but over the space of 45 minutes, over the space of 4 hours, that is kind of modest. And remember, we're still running the simulation at a much smaller time step. Let's see how many seconds to run before plotting. Okay, and we're going to have our record defined as the plot cycle time divided by the time step. This will be how many cycles to run between plots. Okay, we will go ahead and set the number of nodes for our line to be 191. This means that the length of our turkey will be the 1.9 or 19 centimeters that we desire, okay, or 0.19 meters. How do we do that? We say, okay, n minus 1 quantity, or quantity n minus 1 times dx, and this will give us the total length in x direction, or whichever direction, but it's a 1D problem here. The x's will then be given by this vector. So these are the vector of positions in x. And n minus 1 is kind of that question of how do you measure the length of a fence when you have to have a post at each end. So we had to add one extra one. So that was, 1.9 or 19 centimeters, 0.19 meters is what we were going for, but we do n minus 1. We will set the temperature across this line to be the thawed temperature of 283 Kelvin. So this is setting the initial temperature across the turkey. Okay. And we will go ahead and specify a temperature at the left of our line to be 436. And this is going to be a Dirichlet left boundary temperature, which matches what we're setting the oven to. So the oven has been preheated, and we're making an assumption here that the surface of the turkey is going to be the same as the oven temperature. Okay. Now we've got a left and a right temperature, and we're going to say that they're going to be the same. We're going to define the thermal property, alpha, thermal diffusivity, for our turkey as being the conductivity divided by the density divided by the specific heat. Okay, so this will be the thermal diffusivity of the turkey, and that's in meters squared per second. And I often, as you know by now, like to just plot the initial conditions and hold it for a couple of seconds to get an idea if I have set things up correctly. So we're going to plot the temperatures across the line, just like you see here, and we'll give it a descriptive title. Maybe a little bit too descriptive for some people's taste, but it's often very good for troubleshooting to have a descriptive title with values that are relevant to what we are simulating. So we're going to put the initial time, which is the 0. We're going to put the time step in there. We'll also put in how frequently we're plotting. That may be a little bit excessive, but probably not. So we're going to do num to string what we call plot cycle time. So this is the time between plots. Of course, our dt must be much, or is generally much smaller than that value, and it can't be greater. That wouldn't make much sense. And we have also the ability to type out what our spacing is, the dx, and that should do it for now. We're going to label our x position, or the x-axis with x position. We're going to make that font size a little bit bigger to make it a little bit easier to read. And we're going to label the y-axis as being the temperature. And we can do a hold off for now, and then we'll just let it sit there for a couple seconds to marinate. So we can go ahead and take a look. This should not be very interesting, but it will give us a chance to see if we made any mistakes. So we'll call it turkey 1D. Okay, so let's try it. What we should get is just a plot with a constant temperature across its profile, 283 Kelvin. This looks pretty good, actually. Okay, good. Let's move on to actually doing the simulation. Well, we're going to iterate in time. So for that, we're going to have an index that we associate with the number of cycles. Remember, we said that our number of cycles could be thought of as the final time divided by dt. Maybe it's more useful now that we're getting down to do this. Okay, so you can see. We talked about this a little bit in class, the use of circ shift to allow us to think about the temperature or some parameter at x sub I plus 1, for example, or x sub I, or at x sub I minus 1. So when we shift t minus 1 here, or we're taking the temperature vector and we do minus 1, this shifts everything to the left. Okay? And so when we do that, the leftmost point would then become the point that was right next to it, to its right before. And so that is useful in terms of being able to call this t1 as essentially the tx sub I plus 1, okay, because we shifted everything to the left. If you want to go back and review this, you can by watching the video of the lecture where we did some examples with the heat equation and initially just showed how the vector was being shifted to the left or the right with these commands. We will want to be able to use the t sub x sub I minus 1 as well. So circ shift t1 will shift things to the right and allow us to do that. Then we bring in the heat equation right here. And this is going to be using a centered difference to approximate the second derivative. Okay, so this is the heat equation. And to review that, because it is pretty important, let's see, where did we cover that? Right about here. Okay, so we realized that we could use finite differences twice and use the Taylor series with the second order term to come up with a method for discretizing a space, and then we have discretized time. And so this is the heat equation in terms of a difference, a centered difference, and we have our txi plus 1 minus 2txi plus txi minus 1. Okay, and if you move that over to the side, you get the tx1 and tx sub 1 added together, and then minus 2 times where you are. Something to also not take for granted is that this is delta t. So delta t refers to thinking about, okay, what's the new t minus the old t? So we can add the old t to the other side. So it would come over here, and then so if we go back to what we have in our MATLAB, what you see is we have this right here, t and t, that represent the delta t. This is kind of the old t, what it was before, and t is going to get updated. Okay, and then this is the finite difference that we saw, the centered difference. Now, we can just run this program if we want, in fact, without doing anything. Maybe, well, let's see, we should at least plot. I'll show you what we can do here. We'll do a plot. Okay. When the modulus of the iteration number and with the record number is equal to 0, and we'll do a plot of x as t. like this. And for the title, we're going to use the same title we had here with a little bit of extra information. So right here, okay, and I'll go ahead and just do a smart indent, Control I. So that's very nice. It makes things look pretty good. Okay, that will line that up. And we're actually going to add one more piece of information here. We're going to make this a little bit messier. We're going to add a mid temperature. Okay, so what does this mean? This means that we're going to plot out the middle temperature at the midpoint of our line in Fahrenheit. Okay, so we have lots of mixed units in this problem, but this will give us an idea if we're getting close to the safe temperature of our turkey. Okay, and we need to define that mid temperature, so we'll do that right here. So mid temp F is going to be a conversion to Fahrenheit from Kelvin, and we also need to find the mid temperature. So first we find the middle. Okay, so n over 2 is going to give us something close to the midpoint, and it's an odd number. And you have that +1, so we'll just do a round, and it will round us up, okay, to the midpoint. Then we are going to subtract, okay, from it the 273.5, and okay, that will work like that. My parentheses good. And then once we've subtracted that, we're going to multiply by 9/5, and we're going to add 32. Okay, I think that will work out okay. Except, oh, not balanced. There, now we're balanced. Okay, and then, so let's just plot this, and it shouldn't be that exciting in reality. Let's see what we get. If we don't, we might get an error too. Okay, and okay, it did give us an error. What did I do wrong? Okay, line 36. Okay. Oh, that's why it needs to be here. No, wait, T round, T of, yeah, it needs to be there, right? Because we're taking a T. Yep, there, okay. There, now let's try that. Okay, and, okay, now there's another mistake. Line 41, mid-temp F. Oh, there's a caps here, there's not a caps here. Thank you. Okay, just like that. And now it's just telling us the middle temperature, and it's supposed to be, did it do it? Plot every 900 seconds. Oh, the time is just the same though because I didn't update this, so this needs to be I times dt. All right, now let's try it. Yeah, so it just went straight all the way up to our temperature. It was not very exciting plot, okay? Because everything is just staying constant. Now, if I started with a different profile, then it would show something kind of interesting. So like if we did this instead, where we said, okay, I'm going to do the 300 plus 30 times, let's just say sine of, oh, I'm getting in trouble because I didn't think about this. Let's say 3 times, or no, 2. Let me see if I have something over here that I can use. You might want to fast forward through this portion. Okay, here we go. Yeah, so I can do it correctly. So 2 times pi divided by L, x times xs. If we do that, right, this will be then simulating how this drops down. Oh, why didn't it show? Oh, because I forgot the draw now. And then I didn't even spell it right. Okay, yeah, so there it goes through the different, and then you can see it drops down. If we do a hold, then it will put multiple. There we go. All right, so you can kind of see the trending behavior. Now, we still don't have something very interesting yet. Well, it is interesting, but it's not relevant to our turkey problem. So what I'm going to do is I'm going to go back and I'm going to get rid of that. And then we're going to specify the temperature at the left and the right. So after we run the heat equation, we can say that the left node is going to be at this higher oven temperature. The left would be the first element, and so we just say that's left, temperature at the left. And this is Dirichlet on left. And then Tn will be Dirichlet BC on the right. Okay. So when we run this, now we'll see that the temperature at the right and the left, it stays constant. That's at 436 Kelvin, which corresponds to the 375 of the oven, okay, in the original problem statement. Or 325 maybe, let's see what I wrote. 325 degrees Fahrenheit of the oven. And then after 4 hours, we're looking at plotting every 900 seconds, and the temperature at the middle, okay, over here about, okay, so you see that it says it's 322 or so, 322 or 119. If you look up here, it keeps going in and out, but if you look up there, 119 or 120 degrees Fahrenheit, that's lower than what we would like for safe cooking. So one might think from this model that we should cook for a longer period of time, which could be the case. Yeah, I've had turkeys where I've had issues knowing how long to cook them. And another idea is that maybe there's something kind of interesting happening with the, let's go down, the way we're simulating this problem. Okay, this is a 1D simulation at this point. What does that mean? That means that if I have a line like this, we're saying that the thickness, okay, could be something slightly exaggerated like this, is some type of block. Okay, that's maybe not the best block, but it's a block. Okay, and we're specifying the temperature. So we're making this, that's, you can't really see the difference, but this is like T left. Okay, and then over here on the other end, right, we're specifying a t right. Okay, but the rest of these boundaries, okay, the rest of these boundaries, if I can, like this boundary, that boundary on the bottom, that boundary there, they're just insulative, which is great. So these are insulative. Okay, and the way we've defined things, right, the temperature boundary just keeps expanding if we go left or right. So essentially what we're saying is this system goes infinitely in all directions, and it's got temperatures applied to the front and the back, or the left and the right here. What it also means that if you have a three-dimensional object, that you don't have the opportunity to apply more heat from the sides. Those are completely insulative. So in a step towards being able to think about the 3D problem, we're not going to do it here, but in a step towards that, if you think about, okay, now I've got the same box, okay, but now I can specify heat flux, or, well, let's not, there are going to be fluxes involved, and we'll talk about that, I think, more in the assignment. But here we can apply high temperature there. We can apply high temperature on the back side, so T high, okay, and we can play, that's really spelled poorly, T high over here, okay, and over on that back side too, T high, okay. So we have the ability to get to more of the inside of the turkey because we can have higher temperatures and essentially higher flux of heat coming in to cook the inside. So what we're saying is right now the 1D problem at 4 hours looks like it's not quite cooked. And for a 15-pound turkey, 4 hours is about the time that is suggested to have a safely cooked meat. But maybe if we do the 2D problem, we'll be able to add heat on 2 more sides, which could increase the internal temperature. So how do we go about doing this? Well, we're going to need to create a mesh, a 2D mesh to do this. And we're going to go back to MATLAB, okay, to do this. What I'm going to do actually is I'm going to do a copy and a paste. Okay, whoops, and then I will make this turkey 2D. Alright, just like that. Alright, so then for the 2D problem, we can go ahead and use the same time step. Okay, we can use the same final time. The dx, we're going to actually make this a little bit bigger so it's not so computationally intensive, because now we have the grid going in 2 directions, right? We have a 2D grid. We can still plot every 900 seconds. It's not that important because we are assuming a kind of a symmetric grid or square grid, but we can say that dy is equal to dx in this case. All right, so this is going to be mesh size and y, but really we can just keep dx and use dx a couple times, which is what we're going to end up doing. And in this case, what we have a mesh that's 5 times larger, at least in one direction, than it was before. So we're going to have 38 plus 1 nodes to get us our Lx. And then for our grid, we're going to go ahead and use this idea of having x's and y's, or x's. All right, so we're going to create y's, which are just going to be equal to x's. So this is a vector in y. And we're going to create a mesh grid. Now, mesh grid is an interesting function in MATLAB, very useful, and also sometimes a little bit confusing. So you might want to spend a little bit of time thinking about this mesh grid and what it does, the function. I do want to point out something. If you go to the slides, which have been updated since the first group, I included some information about how the grid is set up. So this is for Dirichlet. Let's see here. Does this work? Yeah. So what we're looking at now is a grid, all right, and let's say this is x and y, and 1, 1, okay, does correspond to kind of the bottom left corner, all right. But when you start pulling things from mesh grid, be careful, because say I'm looking at temperatures on this mesh grid, T of 1 comma n is over here. It's not the first, right? You normally say x, then x comma y, right? No, the way mesh grid sets things up is actually running through the second component here. So note that T of ij, okay, so if I put, a 1 or n here, it's telling me essentially the temperature at x sub j comma y sub I. All right, so just be careful about how we figure out and address these different points. So going back to MATLAB, okay, let's continue to edit the script. We're going to now have our mesh, and we'll call our ambient, now we don't have a T left and a T right. We're just going to call this, we'll just call this TA. Okay, so this is going to be our ambient Dirichlet ambient temperature. Okay, which is the surface temperature. We're assuming is the surface temperature. Okay, and we're going to set up the initial, and so before we had T lin space, okay, we had those, but now we're going to say that the initial setup is going to be equal to a matrix, okay, made of all ones. So this is every element, okay, in this n by n matrix is made of ones, and then I can multiply by the initial temperature. It is just uniform. Okay, so now it's a matrix, an n by n matrix full of 283. So this is uniform initial temperature. Okay, and we have the ambient temperature. We should, let's see, we already have our alpha, so we don't need to change that. That stays in there. We need to plot things a little bit differently, so we can take out the plot, and then we can use mesh. Okay, so x, y, t, temperature, and we can do an interpolative shading, and we can also have a color bar. But other than that, we can still plot everything else as it's been plotted. In here, okay, we still are going to use the heat equation, and the circ shift changes just a little bit. Okay, for this, what we're going to do is still have a shift to the left, but we need to put in, since it's a matrix instead of a vector, okay, we're going to specify that we're not changing the y component with a 0. And we better call that x. And then we'll call this x of 1, and we're going to, as you can imagine, shift to the right. And then we can do a shift upwards. specifying it like this. Okay. So this is going to be T shifted upwards, and this is going to be it shifted downward. Okay, great. The main heat equation is going to change just a little bit. What we're going to do is apply it twice. Okay, now you can do it in one step. If you look at Professor Singer's videos, he did it in one step. But I think it's not bad to kind of do it in a two-step fashion. So we have the heat equation being applied in the x direction, and then we can take that result and apply in the y direction. So we're doing two centered difference manipulations of the temperature grid with the Laplacian. Okay, and so this is heat equation in x, and this is the heat equation in y, just like that. Okay, now before we do this, these manipulations, okay, the manipulations are starting now in line 45 and continuing 46. I want to preserve what the temperature was, this T, so I can, before I can specify a T old, okay, and so now yes, these will get manipulated through the Laplacian, which is fine, but if I want to get access to what it was at the beginning of this time step, before, because this is going to do a periodic boundary. Okay, it's going to cycle through the top and left, and it's going to just flip those things. So if I want to manipulate the temperature, okay, I might want to keep track of what it was old. Okay, and that's more important for Dirichlet or for Neumann. Okay, but here we don't need it. So now we're going to do fixed temperatures. So this is where Dirichlet comes in. So this is going to be, so 1 comma, that means all. Okay, so remember, this means actually that we're doing the bottom, okay, because 1 it would be for the y, and then we've got all the x's taken care of, and we're going to set that to our ambient temperature. So this is Dirichlet for the bottom. Okay, this would be Dirichlet for the top. And this one is going to be Dirichlet for the left side. And this one is going to be Dirichlet for the right side. Okay, and all we're doing is setting that temperature. Okay. For the plotting, and I'll get rid of these, okay, because those were good, but they were good only for 1D case. Okay, so this, for the mid temperature, we actually have another component. We can say we're going to take it at the middle, so round n over 2, comma n over 2. And that will give us the middle. And then for plotting, let's go back up and see what we had here. We have mesh, dot, dot, dot. All right, good. And we can put that here instead of plot. Just like that, except not like that. Control A, Control I, everything looks good, at least in terms of indents. Let's see what we get when we run this. and how many errors we get. Oh, did it not run? Is it? Oh, it's busy. It's thinking. Okay, what's it thinking about? Okay, so here's the initial. Okay, it didn't like this. Why didn't it like this? Okay. Oh, unrecognized. Oh, because I made a typo here. Let's try that now. Running again. Okay, so it's plotting every 900 seconds. It might be a little bit hard to see what's going on. In fact, okay, so we got to the end, okay, the 4 hours, and it says that the middle temperature is 172 degrees Fahrenheit, all right, which is promising. If we go around, okay, you can actually kind of put it right here, and 283 Kelvin, all right, 283 Kelvin is corresponding to that 172.3 635, whatever it is, 35 degrees Fahrenheit. Okay, so what are we looking at here? I mean, we can also move things around and look down from the top, right? Essentially, we have the heated walls, right, and they're at 436. Okay, so up here, and then we saw that this middle, okay, is behind in terms of the temperature, right? And in the middle, we're at 350. Wait, what did I say? What is it looking? So that's an interesting. Okay, hold on a second. Yep. Okay, so I do believe that the 173 is correct, but what it's doing, the reason it didn't change is because it left the hold on. Okay, so that was low. I'm sorry. So let's take the hold off so then we can see what happens more clearly, because that 283 is just 10 degrees Celsius, right? So that's me not being very wise. Okay, so now that we got the hold off, now we can see the individual plots and we can see the progression to 4 hours. And so now, if we move around, okay, here, now it's 351 degrees, okay? And that 351 degrees corresponds to 172. This number was still right, it's just what we saw and what I selected were not, okay? So, yes, from this model, once we do the 2D model, we can say that it appears that the meat of the turkey in the middle would be pretty safe. It's over 165 degrees Fahrenheit. Maybe we should go for a little bit less time. So if we do that, if we went for 3.75 hours, okay, so we go for 15 minutes instead of 3 hours and 45 minutes instead of 4 hours, then our simulation will tell us that the temperature in the middle will be less at 162 degrees Fahrenheit. So maybe a little bit slightly under, right? So maybe a little more tender meat, not quite the 165 degrees Fahrenheit. So something in between is probably a happy medium. Well, I hope you found this session interesting. For your deliverables, okay, what we're asking for are a 1D simulation run for some period of time, and then a 2D, the results, or 3D plot for the 2D simulation run for another period of time. And just put those in a single PDF and submit them. All right, thank you very much. Have a good day.